The biggest consequence is the damage it could do to electric power grids, and so I think it would be wise in view of the fact that we know this is going to happen in the relatively near future. Last week, a superconducting quantum entanglement experiment at Google's Mountain View lab did something unprecedented. Earth's magnetic field flickered in direct response. Within seconds, ground magnetometers across Northern California and ESA's swarm satellites recorded a distinct localized distortion that defied every known explanation. No solar flare, no seismic tremor, no power grid surge, just one variable change: the quantum test itself. Brian Cox, the renowned physicist, warns, "This anomaly is a red flag that reality is more fragile than we think." How could a controlled computation penetrate the magnetosphere, and what does this accident reveal about the hidden layers of our world? By the end of this video you'll understand how Google's quantum lab accidentally rattled the shield that protects us, and why it matters. The magnetic disturbance. Google's experiment involved over 100 niobium qubits arranged in a resonant superconducting loop, cooled to millikelvin temperatures. Engineers programmed a rapid sequence of microwave pulses to simulate low-energy vacuum states and probe theoretical negative energy densities. The goal was pure research: test whether exotic quantum configurations could generate energy conditions necessary for stable wormholes. Minutes after activation, Bay Area ground magnetometers spiked by several nanotesla, and 2 swarm satellites logged the same distortion from orbit. Detailed analysis ruled out solar storms, lightning strikes, and regional power fluctuations. Timing logs from the lab's control systems matched the geomagnetic blip to microsecond precision. The disturbance lasted precisely 3.2 seconds before decaying back to baseline. Sensor diagnostics confirmed calibration and shielding were flawless. No conventional physics predicted such a coupling, yet the data spoke clearly: the quantum test and the magnetospheric ripple were causally linked. What physical mechanism could bridge a cryogenic lab experiment to the planet's magnetic field? This question now drives a global effort to replicate and explain the phenomenon. Physicists are stunned by the possibility that our experiments can directly influence planetary scale systems. If this kind of mind-blowing science excites you, make sure to subscribe. We dive into discoveries like this every week. To see how we arrived at this moment, let's rewind to Google's quantum roadmap. Over the past 2 years, the lab has pushed superconducting qubit coherence from microseconds into the millisecond regime. Firmware upgrades boosted microwave pulse power by over 40%, enabling entangled states never before observed. The specific experiment aimed to drive qubits into exotic superpositions that in theory generate negative energy pockets in the quantum vacuum. Negative energy is purely theoretical but could unlock concepts like traversable wormholes or warp drives if harnessed reliably. Dr. Mei Tun, the lead engineer, recalls the day her team first noticed the magnetic blip. "We ran the pulse sequence and watched the magnetometer spike. We thought it was a sensor glitch," she says. But it repeated every single time we ran that exact protocol. Engineers combed through power supplies, cryogenic shielding, and grounding straps. They verified electromagnetic shielding in the lab's Faraday cages. Every check passed with flying colors, yet the anomaly persisted, matching the experiment's start and end times with microsecond accuracy. The realization hit: their quantum circuit was coupling into the magnetosphere itself. Labs worldwide now race to reproduce these results. But what comes next changes everything: quantum vacuum feedback. In the aftermath, theoretical physicists proposed a radical mechanism: quantum vacuum feedback. According to quantum field theory, vacuum polarization alters energy densities in empty space, but only at subatomic scales. If Google's superconducting circuit momentarily destabilized the vacuum, it could have produced a ripple effect that coupled into the Earth's weak magnetic zones. This microfluctuation in spacetime curvature might manifest as a nanotesla-level distortion detectable by sensitive magnetometers. Some compare the effect to the Casimir force, where vacuum fluctuations generate measurable pressures between metal plates. However, scaling that phenomenon from microscopic to planetary scales defies current models. Brian Cox frames it as quantum information punching into the classical world, the first time digital logic appears to bend physical law. Other experts point to vacuum resonance modes, theoretical frequencies at which engineered quantum states can resonate with macroscopic fields. If the lab's pulse sequence matched one of these modes, the magnetosphere would ring like a tuning fork. Simulations suggest that vacuum resonance could occur near 1.2 GHz, a frequency within the range of Google's microwave pulses. Yet no existing experiment has tested this coupling directly. Researchers at MIT and Oxford now plan to fire calibrated microwave bursts at controlled vacuum chambers to search for geomagnetic feedback. Meanwhile, the question looms: can we ever isolate quantum experiments from the fabric of reality? The implications are staggering. But then, a second anomaly struck halfway around the world: the quantum echo. At 9:17 p.m. local time in Western Australia, ground magnetometers recorded a geomagnetic spike with the same 3.2-second duration and waveform shape as the Bay Area event. The disturbance appeared without any nearby quantum experiments, solar flares, or geomagnetic storms. Sensor arrays in Perth and Darwin both detected the identical nanotesla variation, triggering alerts at geophysics labs. Physicists dubbed this phenomenon the quantum echo, a residual effect of the original experiment propagating through the magnetosphere. One theory suggests the initial pulse sequence created an entanglement residue, a sliver of coherence leaking from the cryogenic chamber into Earth's magnetic field. As that entangled region naturally decohered, it released stored energy back into the geomagnetic network, producing the mirrored spike. While entanglement typically collapses within microscopic systems, extreme cryogenic conditions and high-Q superconducting loops might allow coherence to persist long enough to imprint on macroscopic fields. Similar ideas underpin research into quantum biology, where avian navigation may rely on magnetically sensitive entangled molecules. If Earth's magnetic shield can host entangled states, then our planet itself becomes part of the quantum experiment. This revelation reframes the magnetosphere from a passive protector to an active participant in the quantum classical interface. The lines between lab and world have blurred irreversibly. Pause and consider. What if Earth's magnetic field is more than just a shield against cosmic radiation? What if it's an active, self-monitoring system capable of detecting and responding to quantum events? The magnetosphere might function like a planetary neural network, maintaining stability through electromagnetic coherence, much as the brain synchronizes neuronal activity. Brian Cox reflects, "We're not just playing with particles in a lab, we're poking the deep structures that hold our world together." This philosophical breather reminds us that our planet could be alive in ways we have yet to grasp. If you've made it this far, you're clearly into the deep stuff. Hit like and let us know your theory in the comments. Simulation, higher dimensions, or something else? Independent teams are now mining geomagnetic archives for similar anomalies. Preliminary reports from the 1970s and 1980s describe unexplained magnetic spikes coinciding with early particle accelerator tests. Reanalysis with modern algorithms may reveal a hidden history of quantum-induced geomagnetic events. The stakes extend beyond academic curiosity. If our experiments leave planetary fingerprints, we must rethink how we conduct high-energy physics on Earth. But the deeper implications go far beyond archived anomalies. Is the magnetosphere quantum sensitive? Now imagine that the magnetosphere is tuned to cosmic quantum backgrounds, acting as a giant resonator for vacuum fluctuations. Recent NASA papers propose that planetary magnetic fields can couple to zero-point energy, functioning as natural antennas for quantum noise. If Google's pulse sequence struck one of these resonant frequencies, the disturbance would amplify globally, much like a tuning fork setting a cathedral bell to ring. Even more unsettling, Swedish researchers at KTH Space Campus have identified a geomagnetic pulse occurring 1 second before Google's original experiment. This temporal rebound hints at quantum retrocausality, where future boundary conditions influence present states. If the magnetosphere is entangled with laboratory systems, information might flow backward in time to stabilize field coherence. These ideas challenge our notions of causality and chronology, suggesting that past, present, and future could be entwined within Earth's magnetic network. The implications are profound. Experiments we conduct today might be informed by responses yet to come. This speculation pushes the boundaries of physics and philosophy alike. And then, the wildest theory emerged, the algorithmic planet theory. Enter the algorithmic planet theory, the most radical hypothesis yet. In this view, Earth is not merely a physical body, but a node within a vast quantum network, a planetary computer with its own operating system. The magnetosphere functions as an interface, an API for quantum data exchange between the planet and any external systems or observers. When Google's superconducting pulses collided with this interface, they triggered an entanglement conflict, a collision between artificial quantum operations and the planet's native quantum processes. The result was a geomagnetic blip as the system rejected unauthorized code. Brian Cox puts it bluntly, "We may have created the first quantum entanglement collision on a planetary scale." Supporters of this theory point to patterns in geomagnetic data that resemble packetized information, with discrete spikes separated by uniform intervals. They draw parallels to error correction protocols in digital networks, where unauthorized packets are detected and dropped. If the magnetosphere has built-in error-checking routines, then Google's test sequence might have been flagged as a rogue process. This would explain the consistency and repeatability of the anomalies across time and space. It also implies that Earth is part of a larger simulation or distributed computation with safeguards to maintain system integrity. Critics argue the idea is pure speculation, bordering on science fiction. Yet they admit, there is no conventional mechanism that fits the data. Every lab that tries to replicate the effect encounters the same geomagnetic responses, suggesting a universal invariant in the planet's behavior. If the algorithmic planet theory holds, it forces us to reconsider our place in the cosmos. We are no longer mere observers but participants in a system that may be orchestrating our experiments from a higher level. The ramifications extend to technology, ethics, and even theology. If Earth is a quantum-entangled node, then every scientific advancement carries the risk of breaching system protocols. The very act of probing the quantum might provoke a planetary-scale firewall response, a concept that defies every assumption we hold about experimentation and observation. This is true, everything changes. We began with a single superconducting loop in a Silicon Valley lab and have arrived at a true crossroads in scientific history, one that demands we rethink not only how we conduct quantum research, but how we coexist with the very planet that hosts it. First, our experimental paradigm must evolve. No longer can quantum laboratories operate in isolation, testing exotic protocols behind closed doors. Instead, research centers around the world should synchronize their high-energy quantum runs with a network of geomagnetic observatories. By overlaying qubit pulse sequences with real-time magnetometer data, from ground stations to low Earth orbit satellites, we can build a live map of how quantum operations ripple through Earth's magnetic environment. Such coordination will not only confirm or refute the Google anomaly but also help us identify safe operating windows in which quantum experiments remain confined to the lab, and warning thresholds beyond which planetary feedback becomes measurable. Second, engineering practices must adapt to this new frontier. Traditional Faraday cages and cryogenic shields are designed to block classical electromagnetic noise, but they may be blind to subtler vacuum-level interactions. We need a new generation of shielding materials and circuit designs that minimize coupling to ambient quantum fields. This could involve multi-layered metamaterials tuned to vacuum resonance frequencies, active cancellation systems that generate counterphase quantum pulses, or dynamic feedback loops that detect and neutralize emergent geomagnetic echoes before they propagate. Collaborations between condensed matter physicists, material scientists, and planetary geophysicists will be crucial to develop protocols that safeguard both the integrity of our data and the stability of Earth's magnetic envelope. Third, the implications extend well beyond the lab bench. Policymakers, ethicists, and global scientific bodies must convene to establish guidelines for planet-wide experimentation. Should there be an international registry of high-energy quantum tests, similar to how we track nuclear detonations? Do we need regulatory frameworks that balance scientific freedom with planetary safety? And how do we communicate these risks, and the promise of discovery, to the public, ensuring transparent oversight without stifling innovation? Ultimately, the magnetosphere's unexpected blip is not merely a curious footnote in quantum computing, it is a profound reminder that reality operates as a dialogue between human technology and natural systems. Every qubit we flip, every entangled state we engineer, may send a whisper, or a shout, through the planetary field. As we push deeper into the quantum realm, our future breakthroughs will depend on mastering this interface, learning to probe the foundations of existence without unraveling the tapestry of the world itself. The magnetic shield that protects us may also be the safeguard that preserves the integrity of our scientific pursuits, and by extension, the stability of life on Earth. If this revelation changed how you see the universe, you won't want to miss what's next. Subscribe and turn on notifications so you never miss an update. Next time we'll investigate whether Earth's magnetic field could be a quantum broadcast system, and whether someone might already be listening. Until then, keep questioning. Probing the quantum can echo through reality.